Okay, so today we're going to be examining the thought experiment called Kant's left hand. Now to understand this, you have to contextualize it within the thought of the day. There was a big debate over whether or not space was a real thing, or if it was merely just a function of matter. And to give you an example, Newton, Sir Isaac Newton, the famous mathematician and physicist, believed that space, or the rest of the universe, was like some sort of grand theater. So we have like here are the drapes, and this the stage. And so no matter where anything was, space was very definite. It had a specific place. It wasn't merely just a function of matter. And I guess we can make more sense of this as opposed when we juxtapose it to Leibniz's view. Leibniz, also a famous mathematician and physicist, believed that instead space was merely a function of matter. So, there is no objective space. It was merely when we said that, I am here, all I'm really saying is I am here relative to all the other particles around me. So instead, he would say that there is no grand theater. It's more just, we say that this, particle is here because we have something, to relate it to. Another particle, or in this case, in our universe, billions and billions and trillions of particles. So it's merely just a function of where everything is relative to everything else. Okay, now Kant was trying to argue in favor of this position, Newton. So we'll write an N for Newton and an L for Leibniz. Okay, so what he was trying to argue was that space was a purposeful thing independent of matter. That even if nothing else existed, there was still a thing we could recognize as space. And he does this by creating the thought experiment, Kant's left hand. Now, I'm going to explain it the way he explained it, and I don't feel that it's really that clear. So then I'm going to give you my own example. So Kant said, imagine there's a universe. And so we can use this as the universe. Imagine there's a universe, and the only thing that exists is a single hand. And he proposed it would be his left hand. His left hand, yeah. So we're going to just draw a little hand. Okay, that's a hand. It's a bad hand, but it's a hand. And now he says, is it a left hand or a right hand? Now, I say, he said it's my left hand beforehand, but that's kind of meaningless in a universe without any other relational object. So, if it's the case that it is his left hand, how do we know that in a universe that only has it? And he says that this account of the universe only makes sense in Newton's view and not Leibniz's. It's still a left hand, but there's nothing else to really relate it to. So how would we know it's a left hand? Now, if that doesn't make any sense, don't worry, I can explain it much better. That's just Kant's formulation of this. A better way of looking at it is instead, imagine we have, let's say, let's try the letter L. Okay. Now, when I was growing up, I'm just going to do an aside. When I was growing up, they said the way to determine your left from your right is do this, and the one that makes an L is your left hand. Well, when I was younger, they both looked like L's to me, because for me, an L was just a downward line with another line coming off of it. So that was kind of meaningless. And in a way, that's kind of how Kant, or not how Kant looks at it, but that sort of should give you an example of how you can sort of make sense of this. We have what we would recognize as the letter L. But in a universe where there is no objective space, these should be identical things. We can know this because if space is only a function of matter, then, okay, so we have one particle right here, another particle right here, another particle right here, maybe another particle right here, another particle right here. We'll do the same here. Okay, so if space is merely a function of matter, then, yeah, we'll put a particle right here. Then, okay, how would we describe these two objects? Well, we'd say, okay, so there's a particle up here, and it is, let's say 1 foot away from the particle below it, but below is kind of meaningless. There's one particle in this direction now, or 1 foot below it, again, below. And then we say, okay, so here there's 1 foot below that one. There's 1 foot below that one. And it just keeps going and going. and then we say, okay, now there's, from this particle, there's space 1 foot between this one and this one, going in a different vector. Okay? So let's write 1. So if we're merely describing it, as Leibniz would, as a function of matter and not a function of objective space, then I can write out the same thing on this side. There's 1 foot, and then in this sort of vectoral relationship, there's another foot. There's another foot. There's 1 more foot below it. If we're merely describing it as a function of where it is in relation to other things, there's another foot that goes off another direction. 1 foot. And so, and we fill in the rest for every sort of gap. If we put it in these terms, these are identical objects. Because there is no left and right in a universe, in Leibniz's universe. So then, if these are identical objects, I mean, we know they're not, but according to this account, they would have to be. So that's what Kant is saying with his left hand. He's saying, according to this account of the universe, where all we're doing is, this is about this far from this finger, and 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 it's, goes out this way. If that's all space is, then our hands should be identical things, but they're not. There's clearly a difference. Namely, one's my left and one's my right. And that's what Leibniz's account can't really grasp. If it's merely a function of matter, if it's merely a function of where one particle is in relation to another particle, then these should be identical, but they're not. And it's that sort of qualitative difference that leads Kant to say that Newton is correct, that there is an objective space that matter is put in. And in that objective space, we can make a qualitative difference between functions of matter that are left or right. Now, we can actually, now this is all within like a philosophical background. What's actually interesting is, you speed up a couple hundred years into the future, Kant is actually wrong. When Albert Einstein comes along, he actually shows that there is no objective space. And now, I don't know the particular physics behind this, but I think it's very telling that even through philosophical argumentation, when it comes to physical or empirical facts, even a really convincing philosophical argument that Leibniz is wrong is actually itself wrong. But again, that's sort of hundreds of years later. Another thing that's interesting to note is that this has practical applications in chemistry, of all things. There's a chemical called limonene, and it is the thing that makes oranges taste orange and limes taste lime. And they are mirror images of each other. It's the same chemical, just one goes this way and one goes this way. Now these are not the actual chemicals, but this is just sort of to give you an example of what I mean. Relationally speaking, all of the atoms are the same distance apart and the same sort of vectors from one another. But one is just a mirror image of the other. So that's actually what makes oranges taste orange and what makes limes taste lime. So there actually is sort of a real world, I wouldn't say application, but a real world example of Kant's thought experiment. Okay, so I guess to sum up, we need to understand what Newton thought, what Leibniz thought, and then how Kant was going to defend Newton. So Newton thought that there was like an objective theater of space, and even if there was nothing in it, there was still space. Leibniz thought there was no theater, there was just matter, and when we said that, that is there, or I am here, really what we're saying is, I am this amount of distance from every other particle in the universe. And that was what space was to him. Kant said, okay, if that's true, then there should be no difference between a right hand and a left hand in a universe without anything. But clearly there is. And so it's that clearly there is, that sort of modus tollens on Leibniz's view that allows us to assume, or allows us to get that Newton must be correct. There must be an objective space. And from that, when matter is put in, we're able to determine the difference between a right hand and a left.